Okay, so let's change that. So it's 1.8 divided by the square root of 40. Okay, so that's approximately 0.28 over here. Okay, so we have our normal distribution. So this is our distribution of sample means. Our mean is the same, so our mean is 8.4. And our standard deviation now is 0.28. So again, it's squished together because we're looking at the mean time of our sample means. So we're not just looking at one mechanic, but at the mean time of 40 mechanics over here. So it just makes our distribution a little tighter, a little closer together. Now it says, find the probability that their mean rebuild time exceeds 8.7 hours. So 8.7 is over to the right, and exceeding means greater. So we're looking at the area to the right. Okay, so we know it's going to be less than 50%. So since we're looking for an area, what command should we use on the calculator? Okay, so we're going to use the normal CDF. Where does our area start? 8.7. It goes to the right, which means there's no value we can enter in on the right. So when that happens, we always put a very large number, like 10,000. Okay. The next thing we enter is our mean, which is 8.4. And then the new standard deviation, which is 0.28. Okay. And by the way, you can do these calculations manually. You can take the X values, change them to Z-scores, and then use the tables to find these areas. But obviously using your calculator is a lot faster and a lot simpler. So this is just kind of the shortcut, and I want to make sure you guys use your technology whenever you can. Okay, it cuts down your amount of errors as well. But if you're doing that, I want to see, what you're actually calculating. I don't want to just see an answer. I want you to write down normal CDF. Here's the lower Z-score or X value, the upper X value, and then put down your mean and your standard deviation so I can follow your calculation. And, that's really important too. If you do maybe just one little mistake, you can still get partial credit, where if you just write down the answer and it's wrong, then it's wrong, right? So normal CDF, so second vars, go down to normal CDF, put in the lower value of 8.7, upper value of 10,000, the mean of 8.4, standard deviation, really important to put the standard deviation of the sample means. So if you're not, noticing that, then you probably won't get any credit. So that's really, really important to understand how it changes when you have the mean time of 40 people. And so over here, the probability or the area is 0.1419. Actually, that would round up to 20. And then over here, the value that's closest is going to be answer B. Now, why is it different? Well, because we did the shortcut and calculated it all on the calculator, so our answer is more exact than the one that's given over there. But since it's open answer on your test, you don't have to worry about matching it. Yes, question?
I noticed that kind of happened a few times on the most recent homework as well. I thought that's normal, but my numbers would always be 100 off or something.
Okay. So the homework should be set where it has different ranges of value, where it should still accept your answer, but if it doesn't, send me an email, take a screenshot, and I can, overwrite your score if I see that there's a mistake on it. I know there was one question where you had to do it manually, but I think all the other ones I remember last year, it would take the answers either way. So if there's an issue, send me an email so I can look at it. Yeah.
I'll do it anyway.
Maybe. But you know what? It's worth a try. Yes.
On the test for Wednesday, will you set .421 for an answer?
Yes.
Okay.
Yes, because it's open answer anyway, so it's not like you have to match. What I want to see is I want to see, what is the area, where is it starting, where is it ending, what's your mean, what's your standard deviation. Again, if we rounded this to 0.3, our answer probably would have been differently. In fact, let's check it. If we rounded it the same way as the standard deviation. Let me go to 0.3 here, because obviously that will make a difference. And that's why I want to see what you're actually entering. Are you entering 0.28? Are you entering 0.3? Because it will change your answer. So over here, it changes to 0.1586. So yes, just tell me what you're doing. If you're doing the correct thing, then you're going to get the credit, even if your answer is slightly different.
So the more you route, the more decimal places that you add, it's more correct. Right?
It's going to make it more exact, yes. I mean, if you're entering 3 decimals, it's going to change slightly, and it will be more correct, more exact. Yes, because we're using a rounded value, and so it depends on your rounding for sure. And that could be an issue too with the homework then.
So like, you necessarily don't know like how many like decimal places to round it to for like each calculation.
Right.
Sometimes you round it to 2, but for your answer it tells you how many to round it to. But I feel like in between you can mess up the value.
Right. And so generally the idea is the more decimal spaces you round, the more exact. So you may want to try having more decimals, but it's also important, like if you're going, rounding in one step and then rounding in the next step, it's really, ideally you want to round in the last step versus, right in the middle.
Keep it
Yes. So in fact, we could even go normal CDF over here. Let's look at what happens when we do this. So instead of putting a rounded value for sigma, we can actually put in 1.8 divided by the square root of 40. Let's see what it gives us this time. So then we're not rounding until the very last step, and now it's 1.459. So we're getting even closer to the actual answer over here. So, yes. But, it's open answers, so you don't have to match answer choices to your questions, but I do want to see what you're doing. So it's really important. You want to get credit, write down your calculator commands. All right, good. So the next one is just asking for the critical value, and this is looking for a right chi-square value corresponding to a sample size of 6 and a confidence level of 95%. Okay, so we want to draw our right skewed distribution over here. We're only looking for the right value, but we'll still, drawing the area in the middle, which is 0.95. 95% in the middle, which gives you 5% in the 2 tails, or 2.5% in each. And that's 0.025 over here, 0.025 on the right. And we're looking for this right chi-square value. The chi-square values do use area to the right, and each table actually tells you how it uses areas. So that's always something to keep in mind. An area of 0.025 to the right. We already used that. Label this value, so it's 0.025 on the right. Our sample size is 6, which means our degrees of freedom is 1 less, so it's 5. So going down to 5, our chi-square value is 12.833. And that's answer choice A. If we were to find the left chi-square value, we would just go to an area of 0.975, and that would give us the left one. So if we were to find a confidence interval, we have to find both the left and the right. But over here, we're just asked to find the right one.
Are we gonna have this, or should we bring this?
Bring this, yes, bring your table.
Okay.
And I'll bring a few extra ones. Okay, so the following confidence interval is obtained from a population proportion. So our confidence interval starts from 0.724, goes up to 0.752, uses confidence interval limits to find the margin of error E. So similar to finding the point estimate, how do we find the confidence, the margin of error? So dividing and averaging it gives you that point estimate. But remember, the margin of error is the distance from your point estimate to your upper limit, and also the distance from the point estimate to your lower limit.
Minus the lower limit, right?
Yes, so yeah, basically taking the range of values and dividing it by 2. So we're going to do 0.752 minus 0.724, and we're splitting that distance in half. Make sure if you're doing these calculations in your calculator, you have to either put parentheses around your numerator, or you can put enter between before you divide. So make sure not to just enter it all in one expression unless you put parentheses. So that's 0.14, 0.014. 0.014, which is answer choice A.
So anytime it says point estimate, it's basically just taking the mean.
Yes. So your point estimate is always your sample proportion or your sample mean. That's basically your starting point. That's the value you use in order to find your confidence interval. And so that's always right in the middle, and that's always, yeah. Usually when we have a survey, that's the value we find, and that's the value we use to build our confidence interval around. Over here, we already have the confidence interval, so we can find it, the point estimate by looking in the middle. We can find the margin of error by taking our range and dividing it in 2. So that's the idea for these 2 type of questions. All right, let's look at number 8. A newspaper article about the results of a poll states, in theory, the results of such a poll in 99 cases out of 100, that's 99%, should differ by no more than 5 percentage points in either direction from what would have been obtained by interviewing all voters in the United States. Find the sample size. Okay, so we're looking for the sample size, and this time we're looking for a sample size for proportion. Okay, it tells us 99 out of 100, that means 99% confidence. It also says 5 percentage points. What's the 5 percentage points? It's our margin of error. So you take the percentage, change it to a decimal. So when we're looking for sample sizes for the mean, our margin of errors generally are larger numbers. If we're looking for a sample size for proportion, these are always very small because our proportions can only go from 0 to 100% or from 0 to 1. So that's why we end up with small numbers for the margin of error. So find the sample sizes suggested by this statement. Okay, for the sample size for proportion, we had 2 formulas. One was where we knew, or where we had an estimate of P, and one where we didn't, or for P hat and Q hat. So if we don't have an estimate for P hat and Q hat, we're going to look at the worst case scenario, which means that P hat is 0.5 and Q hat is 0.5. Right, so our formula for that is N is equal to Z alpha half squared times 0.25, that's the 0.5 times 0.5, divided by the margin of error squared. Percentage means we look at z-scores over here. So let's look at the value that's associated with 0.5 .99, and it's actually one of the ones that's listed on your formula sheet. But I'll just go through the calculation anyway. So we have .99 in the middle. We have, that gives us 1% in the tail, or 0.5% in each tail. Now we're adding these two areas together, and then we're going to take the inverse norm. So inverse norm of 0.995. This is one of the other values that's rounded to 3 decimals. So that is equal to 2.576. Actually, on our formula sheet, it says 2.575. So z alpha half squared is 2.575 squared times 0.25 divided by 0.05 squared. So 2.575 squared times 0.25 and then divided by 0.05 squared. We have a sample size of 663.06, and again we're rounding up to 664. Okay, so obviously if you rounded this to 2.576, you may get a slightly different answer, and I'm happy with that as well. So the weights of the fish in a certain lake are normally distributed with a mean of 20 pounds and a standard deviation of 9. If 9 fish are selected, randomly selected, what's the probability that their mean weight will be between 17.6 and 23.6? Okay, so we're looking at a sample of 9 fish and we're looking at their mean weight. So what happens over here? Yes?
Sorry, I have a question about the inverse norm, going back to the last one.
Uh-huh.
How do we know when we need to change the other two values that it asks us?
So if we're trying to find critical values like these z-scores, the z-scores go with a standard normal distribution, okay? Which means that our mean is 0 and our standard deviation is 1. The type of question, actually the next one is the type of question where we have a normal distribution which does not have a mean of 0 and a standard deviation of 1.
And it would tell us.
It will tell you in the question, it'll say it's normally distributed, and then it gives you the mean and the standard deviation,
Okay.
so you know it's not a standard normal one.
Okay, and if it doesn't have those things, then we'll just leave it 0 and 1.
Yes, exactly. So since we have a sample of 9, again, what happens to our standard deviation?
You have to make it smaller, so you have to divide it by the square root of n.
Right, exactly. So we have our mean, which is 20, and we have our standard deviation, which is 9. And then we have our mean of our sample means. And what's this mean of the sample means?
9 divided by the square root of n.
Okay, that's the standard deviation. Our mean is the same. So our mean stays unchanged. So it's still centered about over the same value. It just gets squished together. So our standard deviation is what changes, which is standard deviation is 9, and then our sample size is also 9. So it's 9 divided by square root of n, and n is 9. So over here, this is 9 divided by 3, so it's actually 3. So this time we end up with a nice round number over here. Okay, we're going to draw the curve. We're going to label it. We put our mean in the middle, which is 20. We have our standard deviation, which is 3. And we want to know what's the probability that the mean weight is between 17.6. So we're going to put that on the left side of the mean. and 23.6, which is on the right side of the mean. So we're looking for this middle area. So we have two x values. We're trying to find an area, which means we're going to use the normal CDF. We put in our lower x value, which is 17.6, our upper x value, 23.6. So this time it's not an area to the right or to the left. This time it's an area between two values. So we just put the lower and the upper value there. And then we put in the mean and the standard deviation, which is our smaller standard deviation of 3. And then we calculate that area. So let's see, second vars, normal CDF, going from 17.6 to 23.6. Our mean is 20. Our standard deviation is 3. And then our probability is 0.6731. Really, it should be if you're rounding it. They did not round it. So they have 0.6730. Remember, probabilities are rounded to 4 decimals. Okay? So you have to look at the type of problems. We've looked over a number of questions, and many times it asked us, what's the probability that one fish is maybe between those two values? And what's the probability that the mean of these 9 fish is between the two values? So if it's just asking for one fish, you would just use the old standard deviation. But if it's looking for the mean value of a group of fish, then you have to adjust your standard deviation, right? So look for that type of problem. All right, let us move on to the next question, which is number 10. It says, find the point estimate of the proportion of people who wear hearing aids if in a random sample of 898 people, 46 people had hearing aids. Okay, so what do we have here? We have a sample and we have an x value. So we have n is equal to 898. And our x value in our sample was 46. So 46 of these 898 people wore hearing aids. So what's our best point estimate for the proportion?
X over N.
Yeah. So p hat is 46, or x over n, which is 46 over 898. So again, it's a super simple question. You're just dividing over here. And so the point estimate is 0.051, which is answer B. And remember, in these type of questions, sometimes it can give you the number of people, like an x value, or it could actually give you a proportion. It could say, 0.05, or 51% of the people had hearing aids, and then build a confidence interval. So sometimes you have to take the p hat and change it to an x value, especially if you're trying to find the confidence interval on your calculator. All right, use the given data to find the minimum sample size required to estimate the population proportion. The margin of error is 0.005. Your confidence level is 96%, and p hat and q hat are unknown. So if they're unknown, we're going to use 0.5 for p hat and q hat. So similar problem to the one before. So z alpha half squared times 0.25 divided by the margin of error squared.
Is that the same as the one crop z interval?
So it's not a z interval. We're actually looking at the sample size.
Oh, okay.
So I mean, they correspond with each other, but it's asking for a different thing.
Okay.
So 96% is not one of the ones that's listed, so we definitely have to find our critical value over here. So we have 96% in the middle, which is 0.96. We have 4% left in the tail, so that's 2% in each. So we're adding these two left z-scores together to get 0.98. That's the area to the left of our critical value, and then we use inverse norm of that. So inverse norm of 0.98. And again, this is, we're looking at z-scores, critical values, so that's the standard normal distribution. So we leave our mean and our standard deviation. And by the way, if your calculator does not have the questions top to bottom, you can actually just do inverse norm of 0.98 by itself, and that will give you this critical values. So you don't actually have to enter 0 and 1 if it's the standard normal distribution. So I know each calculator is slightly different. And so we have a critical value of 2.05. So 2.05 squared times 0.25 divided by 0.005 squared. And so let's put this in, 2.05 squared times 0.25 divided by 0.005 squared is a sample size of 42,025. And this time, that's the exact number, so obviously we don't need to round there because it's already exact. Okay, so the next question is similar. It has a margin of error of 0.04, confidence level of 95%.